Welcome to the fourth and final example for the applications of differential equations. In this example, we're going to look at logistic equations. But before we understand what they are, let's talk a little bit about exponential growth and decay, which we're focused on primarily so far, and let's relate it to what's currently going on with COVID-19. We know that initially, we start off with almost no cases. Right, so early days, not many of the population are infected. But as time goes on and more people become infected in the population, then the rate of increase starts to change as well, right? It's exponential growth for you. And suddenly it looks like we're heading vertical. And this is what we've seen so far. However, it can't go on like this forever. Right now, even if it just runs its own course and we don't worry about any of these extra factors, you still get less and less people becoming susceptible, less and less susceptible people because more of the population are already infected, and so there's a lower chance that they will come in contact with someone. So you get this natural plateau. So you get like this inflection point here, and then it starts to plateau off. This curve here is called a logistic curve. So let's have a little look at the equation, the differential equation that represents this. We have dp dt is equal to kp times n minus p. So what is this n value? Because we know p is to do with the population and k is our constant. This n is what's referred to as the carrying capacity or the limiting condition. So you can see in what I've drawn here, we've got this value that we're approaching. So this is our n value. Try and make this horizontal. Now, sometimes the logistic equation is written in a slightly different way, where here you can see another constant is used, capital K, and in this case it's called the limiting condition. So let's just summarize under both of those. So whether we're talking about COVID-19 or something else to do with epidemiology, or whether we're talking about population growth or things in biology or economics, this logistic equation is a more realistic model. Because we generally have some restriction, what we've called the carrying capacity or the limiting condition, in real life. Okay, let's get into our example for this video. Josh sets up a new salmon farm, as you do, with 250 fish. The differential equation for P, which is the population of fish, is given by dp dt equals 0.0024p times 1000 minus p. So for part A, we need to show the following. So we have this single fraction on the left, 1 over 0.0024p outside of 1000 minus p. We need to show that that is equal to 5/12 outside of these two fractions, 1 on p plus 1 on 1000 minus p. So it looks like we've just got an algebraic manipulation we need to do here. Now remember, with show that questions, it's common to start with the left hand side and manipulate it until we get the right hand side, but we don't always have to do that. And in this particular case, looking at these two separate fractions, I would prefer to start with the right hand side, combine these into one fraction, and see if we can get the left hand side. And look, sometimes you manipulate both sides and you meet in the middle. But let's start with the right hand side. So our right hand side is 5/12 outside of 1 on p minus 1 on 1000 minus p. And the first thing we want to do if we want to combine these fractions in the brackets here is create a common denominator. So we'll leave the 5/12 alone for a bit. To create this common denominator, we are going to multiply the first fraction by 1, but the way in which we write 1 is the key. We're going to write it as 1000 minus p over 1000 minus p. And then for the second fraction, the 1 on 1000 minus p, we're going to multiply it by 1 as well. But the way in which we'll write 1 is we're going to multiply by p on p. Okay, so we can see by doing this, we will get a common denominator of p outside of 1000 minus p. So p outside of 1000 minus p. That'll be our common denominator. And now let's have a look at what happens on the numerator. Well, one lot of this is simply 1000 minus p. And then we have minus one lot of p. Minus one lot of p. Oh, my bad. This is meant to be a plus back here. Right, so it's a plus. So transcription error from me, sorry. So let's update that, plus. And that actually makes things quite nice, doesn't it? Because we get the negative p and the plus p, which are just going to cancel each other out. So giving ourselves a little bit more room and updating our equation, we get 5 lots of 5 over 12, sorry, out the front, and then simply 1000 on the top of the fraction, and p outside of 1000 minus p on the bottom of the fraction. Now remember what we're aiming for. The left-hand side had a fraction that involved p outside of 1000 minus p on the denominator. So we're really close. We've just got to fiddle around with the numbers that we see here, the 5/12 and the 1000. So let's multiply the 5 and the 1000 first of all to get 5000 on top of our fraction. And then underneath we have 12p outside of 1000 minus p. But we just want a 1 on the top. So we can divide 5000 by 5000 to turn that into a 1. But whatever we do to the top of the fraction, we're going to do that to the bottom as well. So we'll divide this by 1000. Now, what is 12 divided by 5000? We've got this 12 here. We want to keep this bit. What is 12 divided by 5000? It is simply the decimal that we're after, 0.0024. So we've done it. We have shown our right hand side is equal to our left hand side. So just writing out that final step and then stating that this is equal to the left hand side. Alright, that's part A done. Use the result in part A to show that the salmon population is given by the following equation. P equals 1000 over 1 plus 3 times e to the power of minus 2.4t. So remember, we're dealing with the logistic equation here, so this does look different to what we've seen previously. Also note the negative here. You might think that's a little bit funny at first, given that the salmon population is going to grow, but keep in mind as well that this is on the denominator of the fraction. So let's start with the differential equation that we know. P to t is equal to 0.0024 times p, and that's outside of 1000 minus p. And we've previously seen how we can solve differential equations to get a solution, and this is the solution we're after. And somewhere in there we're going to use the result of part A. Now, like we've done previously, we will need to flip both sides so that we can integrate with respect to p. So we get to t to p is equal to 1 over this whole thing. So maybe now you're starting to see where part A might come in handy, since this was the left-hand side of our part A question. So we'll go ahead and put in our integral signs. Right, we're integrating both sides with respect to p. The left-hand side just gives us time, since the integral and the derivative cancel out. And how are we going to integrate this thing? See, this is pretty scary. We can't just go straight to a log question here, because we've got p and then outside of p again. But if we use our substitution from part A, we'll notice that the right hand side is something that's a little bit nicer. And here is where we would reference that we've used part A. Now, first of all, to make things a little bit easier for us, let's drag out this constant value of 5/12, and then we'll be able to focus on the integral of 1 on p, and then the integral of 1 on 1000 minus p. We can focus on them separately. Let's start with 1 on p. We know that this is the natural log of the absolute value of p. Then we're going to have the natural log again. However, look at this as a chain rule. Look at the bottom here. What's the derivative of 1000 minus p? Because of this minus here, the derivative would be -1. And so we need to be really careful with this. If we were to adjust so that we got what we wanted, and we had a minus there, we would need to counteract that with a minus here. And so we actually need to change this from a plus into a minus. Now we can take the natural log of what's on the bottom, 1000 minus p. And let's not forget our constant of integration plus c on the end. Now remember, whether you put the plus c in the brackets or outside the brackets doesn't really matter, okay? Because even if we had it inside the brackets and we did 5/12 times that constant, that's still just some constant. But we're not done yet. We need to make p the subject of our equation. At the moment, t is the subject. So let's begin the process of making p the subject. First of all, we'll subtract the constant c from both sides. And is there anything we can do with these log functions? Remember, our log laws tell us that if we have log of one value minus log of another value, we can combine them into a single log expression, and we use division. Still include our absolute values there. Next, we want to get rid of this 5/12, so we're going to multiply by the reciprocal. So I'll multiply both sides by 12/5. How do we get rid of a log function? Well, we take the exponential of both sides. Okay. But what we've got on the right hand side is a little bit messy. Might be nicer to use decimals here for our working out, so that we don't have these tiny little fractions up in our power. So 12/5 is the same as 2.4. But when we take the exponential of both sides, this is where we can dispense with the absolute value signs. So we get e to the power of 2.4t minus 2.4c, and that's equal to just p over 1000 minus p. Now to split our exponential on the left hand side. So we have e to the power of 2.4t, and that's multiplied by e to the power of negative 2.4c. Remember, whether we keep this minus or not doesn't really matter, because we are just going to call that some new constant a, still multiplied by our e to the power of 2.4t, and this is of course still equal to p on 1000 minus p. How are we going to find the value of a? So it's really good. We've got p, and we want that to be in terms of t, so that's excellent, but we've got this value a. So we need to think about some of the conditions that we were given in the original question. And that is that at the start, when Josh set up this salmon farm, he started with 250 fish. So population is 250 at the start when time equals 0. So let's sub this in and see what happens. We have a times e to the power of 0. Right, so that'll just be a. And on the right hand side, when we substitute in 250 for p, we have 750 on the bottom, and 250 out of 750, well, that's just 1/3. So a is 1/3. So let's rewrite the equation with this updated value of a. One-third times e to the power of 2.4t is equal to p over 1000 minus p. Can we stop there? No, not quite. Remember, we're still trying to get p by itself. And at the moment, we've got it in two different places. So what are we going to do? Well, ultimately, we need to try and collect like terms of p together. So if we can get rid of this fraction by multiplying this over to the other side, okay, and preferably let's get rid of this fraction as well, we might have some joy. So we are going to have e to the power of 2.4t. It'll be multiplied by 1000 minus p, and when we multiply both sides by 3 as well, we'll get 3p on the right hand side. We're trying to gather the p terms together. So we can see here with 1000 minus p, if we can get that by itself, we'll be able to just add p to the right hand side, so that we'll have a chance at gathering the like terms together. But we've still got this e times to the power of 2.4t. So let's divide both sides by that. But so that we're not dealing with a fraction, let's just think of this as e to the power of negative 2.4t. And over on the left hand side, we just have 1000 minus p, and so now we can add p to both sides. We have 1000 equal to p plus 3p times e to the minus 2.4t. And finally, we're at a stage where we can drag out a common factor of p, and we're left with 1 plus 3 times e to the power of minus 2.4t. One more step to go. Let's divide both sides by this brackets, right? Now also do a switcheroo just to get the p by itself on the left. We get 1000 on the top, and this guy 1 plus 3 times e to the negative 2.4t on the bottom. And that is exactly what we've been trying to prove in part B. Phew, alright, on to part C. Find the population after 2 years, first of all, and then 5 years, second of all. So we have the equation for the population. So we can go and use that and substitute in t. So for part 1, when t equals 2, let's see what happens when we substitute that in to our equation for population. So that is 1000 over 1 plus 3 times e to the power of negative 2.4, and our t value is 2. Using the calculator, we need to be careful that we put everything in correctly. So we have 1000 on the top, and then down here we have 1 plus, and I would personally go and use some brackets here just to be sure. So we've got 3 times e to the power, now this is a negative power, and then 2.4 times 2, I'm just going to write that as 4.8. And then we want to close up our brackets there. So we get 975.9. Now, that's to 1 decimal place. Okay, so let's say that because we're talking about fish here, about population, that after 2 years, there's about 976 fish after 2 years. Okay, what's it going to look like after 5 years? So for part 2, we want to basically do the same thing, but now we're substituting in 5. And once again, we could go and put it in the calculator, being careful with what we do. But let's jump straight to the answer. 999.98 to 2 decimal places. So we can see that for all intents and purposes, it's 1,000 fish if we round after 5 years. So in the first 2 years, we've gone from 250 to 976, but then in the 3 years after that, we've only jumped up another, 24 fish. And compare that to our original curve, we see that with the logistic curve, when you get an explosion early on, but then it just dies off again, right? This S shape, and that's what we're seeing here. Alright, on to part D, the final part of our final example. What is the maximum possible population of fish for Josh's salmon farm? Now, you might already have a little inkling as to what that is, based on what we just saw in part C, but how can we show this algebraically? Well, there's actually 2 ways to do this. The first is by noting that the differential equation we were given is in the form of p to t equals some constant value times p outside of n minus p. And what did we say n is? Well, that is the limiting condition or the carrying capacity of a given population. And so we can link that to 1000. So we can see here that N, the carrying capacity, is 1000. So that's one way, a nice easy way to do it, okay, to see what the maximum population is. The other way is to use our population equation and see what happens as we take t to approach infinity. As t approaches infinity, what happens to this exponential on the bottom here? Well, this is going to approach 0. Right, so negative. So it's going to approach 0. And so what does that mean for our overall fraction? It means that p is going to approach 1000 over 1 plus 0. Okay, and that's just 1000 over 1, which is 1000. So we can apply limits as well to solve this question. I like the first way personally, but it's good to know both. Well, this time for real, well done. We've made it to the end of the differential equations videos. Great job.